Okay, last time we talked about parabolas and we introduced the idea of the vertex of a parabola. Okay, what I'm going to do in this video is actually create a formula for the vertex of a parabola. What I'm really essentially doing is going to be completing the square, or the process we saw last time in the previous video, but I'm going to be doing it in complete generality. Okay, so this way I don't have to go through that completing the square process every single time. Nevertheless, I do want you to be aware of that process of completing the square, because we're going to be using it in the future and other types of problems. And we're also going to be, I'm going to be asking you questions on exams just to, to find the vertex of a parabola using the completing the square method. I will also be asking you questions about finding the vertex of a parabola by using the formula, which is what I'm going to be introducing now then. Okay, so let's go ahead and consider this here. Suppose that I have a parabola here. I'm imagining it, the equation of that parabola being y equals f of x equals ax squared plus bx plus c, like usual. Remember that the leading coefficient can't be 0, otherwise it's not a parabola. Okay, so a is not equal to 0. And now you remember that we could use that completing the square method to always rewrite such a quadratic function this way. Y equals f of x. It's still f of x, but just rewritten differently. A times x minus h squared plus k. And that's what we were doing in the previous video, okay? Now, we saw that we could always do that using that trick, okay, of completing the square. Now, I just asserted in the previous video that the h and the k that you get here when you do this are actually the coordinates of the vertex. So the first thing I want to do before even giving a formula for the vertex is to actually prove that assertion, to show you that the hk is actually the vertex of the parabola. Okay, so that would mean that hk is what? It's actually the low point on the parabola if a is greater than 0, where the parabola is opening upwards, or what? It's the high point on the parabola if it's frowning. That's where a, the leading coefficient, is less than 0. Okay, alrighty. Okay, so to prove that, here's what we're going to do. I first want you to note that f evaluated at h would be what? Okay, so if x is equal to h in this formula up here, okay, just replace x by h everywhere, and you will get that y equals f of h is equal to a times h minus h squared plus k. But you can see that h minus h is 0, so I've got a times 0 squared plus k, you could see boils down to k. Okay? What this means then is certainly h comma k is a point on the parabola. Okay? Now, I'm not imagining that the h and k are the coordinates of the vertex right now, right? Just to re-emphasize, they're just the values you get by completing the square up here. Okay, so we're actually trying to show that those that point is actually the vertex of the parabola. So the first thing I did was what? Show that hk is actually a point on the parabola. Okay, so that's a step in that direction, but we never showed that it's the higher low point with respect to y on the parabola, but we're going to do that now. Okay, but anyway, so hk is a point on the parabola. Okay, I'm going to consider two cases here. The case where what? The parabola is smiling, right? Where it's going upwards. Okay, that's where a is greater than 0, you remember? Or whether what? It's frowning here, okay? And that's where a is less than 0. Now, in the case where a is greater than 0, okay, I am going to be attempting to show that the point hk is actually a low point on the parabola with respect to y. So it's a y minimum, okay? Now, here's what I'm going to do. Suppose I take any value of x, I don't care what it is, but that value of x is different than h, okay? So that's all I'm asserting right now. Suppose you take any x value, just make sure it's different than h. Okay? Then you observe here that what? X minus h would have to be different than 0, right? That would have to be non-zero. Okay? But what if I take x minus h squared? Okay? Well, if x minus h is a non-zero number, what happens whenever you square a non-zero number? Okay? You're going to get a positive number, right? Because if x minus h is positive, its square is positive. But if x minus h is negative, its square is positive still also, right? So this would mean if x is not equal to h, then x minus h squared would be positive, okay? Now, I'm going to go like this. What would a times x minus h squared have to be? Well, here's what I'm doing. I'm multiplying a and x minus h squared, right? You see that in this case, those are both positive numbers. A is greater than 0, that means positive, right? X minus h squared is positive. The product of two positive numbers here, right, that's product here, times, would be what? Positive, so that would be greater than 0. And then if I add k on both sides of this, remember how inequalities work from your previous classes here? I can simply add on both sides of the inequality the value k, and the direction of the inequality will not change. So that I've got what? A times x minus h squared plus k is greater than k. Okay? But take a look at this. A times x minus h squared plus k, that's the function evaluated at what? X, right? All right. What did we say k was? Remember, we just showed right above that k is actually equal to f evaluated at h. Okay? So let's put this all together. Now think about it. If x is different than h, then the function at x is greater than the function evaluated at h. What does that mean then? That means that what? F of h, which is k, is a minimum value, or a minimal value, that y equals f of x can assume. Okay? So if that's a minimum value here, then the hk is what? Is a y minimum point, but that would be the vertex. Okay? So we indeed showed that hk is the vertex in the case that the parabola is opening upwards, where it's smiling. That is the case where a is greater than 0. Let's consider the second case. It's going to be very similar to the first, but I've got to show what? There I'm going to show that it's actually a maximum point. Okay? The argument's very similar as I just stated. Okay, we're under the assumption that a is less than 0. That is, a is negative. If I take a value of x that's different in h, then x minus h squared is still positive, like we observed above. That has nothing to do with a. Okay, but if I go a times x minus h squared, I'm actually going to get a negative number. Why? Because a is negative, but the quantity x minus h squared is positive. A negative number times a positive number is a negative number, and so we could say that that product is less than 0. That's what it means to be negative, right? Now, if I go ahead and add k on both sides here, I've got, once again, a times x minus h squared plus k on the left, but I've got it's what? Less than k on the right, okay? But once again, that is what? The function evaluated at x. And what? The right-hand side is the function evaluated at h. Okay, so that's always true. F of x is strictly less than f of h. So, briefly, or succinctly, if x is different than h, then the function evaluated at x is less than the function evaluated at h. Thus, hk is a y maximum point, and hk has to be the vertex then. Okay, so we showed that the hk, in the case where it's frowning, is a maximum, y maximum point, so that hk has to be that guy sitting right up there. Okay? Alrighty? So there we go. So what I'm showing here is that if I do write this thing this way, then I'm justified in picking off the h and k and calling them the vertex. That was the fact we were using in the previous video, but I did not prove it. Okay, I didn't want to lay on too much at once there, but there's the idea. Okay. All right. Now that we've got that out of the way, let's actually talk about the formula for the vertex. Again, we're in this situation, ax squared plus bx plus c, a is not 0. Find the vertex. What I'm simply doing is completing the square like we did in the previous video, but I'm doing it in complete generality here. Okay, so I've got f of x is ax squared plus bx plus c. Do you remember what we did? We take the leading coefficient, the coefficient on the x squared, and do what? Divide it out of the two x terms. That should be the first two terms if you've written it in descending order like I have here. When I factor out the a, I've got a times the quantity x squared plus b over a, x plus c. Okay? Notice this is a valid equal sign here because what? If I was to use the distributive property, the a would multiply on the x squared, giving ax squared. The a would multiply in the b over ax. The a's would cancel, and I would have bx, and then the c sitting here. So that's a valid equal sign. Now, do you remember what we did here to complete the square? We looked inside the parentheses, and we did not what? We took the coefficient on x, cut it in half, and squared it. Now, the coefficient on x I've written this way, b over a, okay? And I'm going to divide that by 2, and then I'm going to square it. Now, it's easy from how fractions work here. That's really b over 2a, right? b over twice the denominator, and then I'm squaring that quantity. Now, when I square that quantity, I would get what? b squared. I would get 2 squared is 4, and then I would get a squared, okay? So this is the magic quantity, b squared over 4a squared, that I want to do what? Both add and subtract inside those parentheses. Now, the first thing you do is add. Okay, so you can see here I went what? Plus b squared over 4a squared, and then I did what? And then I subtracted it. So these would cancel, and we'd be right up back here. Okay, of course we don't want to cancel them. That's the exact opposite of what we want to do. Okay, but this is just showing that this is valid here, right? This is still f of x, written in a weird way, but it's still f of x. Okay. Our next step in completing the square was to take this guy being subtracted, minus b squared over 4a squared, and take him outside what? The parentheses, right? Now, when I take him outside the parentheses, what I have left inside the parentheses would be x squared plus b over ax plus b squared over 4a squared, okay? So I'll put that in parentheses there, as you see. Now, when I take this guy out, don't forget everything inside the parentheses is being multiplied by a. So I'm actually got what? Outside the parentheses, minus ab squared over 4a squared. And then I've got my plus c there. Now you can see in the next step here what I've done. Inside, you've completed the square inside the parentheses. So these three terms here should form a perfect square. And in fact, if you think about it, it's actually the square of x plus b over 2a. X plus b over 2a. If you square x plus b over 2a, you'll get precisely what's inside the parentheses above. Okay? And over here in this term, I've canceled 1 power of x in the numerator and denominator. So I've got minus b squared over 4a. Okay? Now, I'm going to be adding these two fractions together here. Two terms. Notice that the c here is not written as a fraction, but I want to get a common denominator with this fellow right here. So what I did was write this way. I wrote that as 4ac divided by 4a. Notice that the 4a's would cancel, giving me the c up here, which is just what I want. But what? I want to retain that 4a in the denominator here because I wrote it this way so I could easily add these two fractions, okay? You need a common denominator to add fractions, right? So f of x now is a times the quantity x plus b over 2a squared, plus, if I add these two fractions, I get the 4ac minus b squared, that's the way I chose to write it, over 4a with that common denominator, okay? If you want to, you could use parentheses right here also. Okay, I'm not going to be using this very long. That particular aspect, that thing inside the parentheses, red parentheses there. Remember that f of x is now written in the appropriate form. It's what? a times x minus h squared plus k, right? This is what I like to call the vertex form of the parabola, because you should be able to read the vertex right off from it, right? Okay, now just compare, okay? I've got x minus h would be what? Minus h would be b over 2a. That means h must actually be what? Negative b over 2a, okay? And then the k would be what? This stuff left over, the 4ac minus b squared all over 4a, okay? All right, so we're almost there. Now, I want you to note here, now we've already shown this, that k is always going to be what? F evaluated at h, if I write it this way, right? K is always f evaluated at h. So k is actually what? The function evaluated at negative b over 2a. So instead of remembering, I'm about to come up with my formula for the vertex, right? I don't really want to have you remember this, that the y-coordinate, the k, is 4ac minus b squared over 4a. I think it's much easier to remember our formula for the vertex this way. Just remember with that what? H, that's the x-coordinate of the vertex, is negative b over 2a. And then what? The y-coordinate is found, that's the k, right? Not by remembering this formula up here, but by just evaluating f at negative b over 2a. So this is our formula for the vertex. We're going to write it this way. So k is f evaluated at negative b over 2a. Now, if you did actually evaluate f at negative b over 2a, you would get this formula up here, okay, the b at 4ac minus b squared all over 4a. But this is much easier to remember here. So that's the only reason I'm doing it this way. Okay, now I put that in a box, so you want to memorize this, okay? You want to remember that for exams, okay? Negative b over 2a, and then the function evaluated at negative b over 2a. Now let's illustrate this, okay? Now we're going to show how much quicker this is than completing the square every time. Let's say I give you this question. Find the vertex of y equals f of x equals negative 2x squared plus 16x minus 1. Okay, just to comment here, a is negative 2 in this, b is 16, c is negative 1, although that's not particularly important. Okay? Okay? Here's what we want to do. We want to evaluate what? We want to find the vertex. We want negative b over 2a. So that's negative 16 over 2 times negative 2, and you can see that boils down to just what? 4. So h is equal to 4, right? That's the x-coordinate of the vertex, so that's 4. Okay, the y-coordinate would just be what? The function f evaluated at the x-coordinate, that is, the function evaluated at h gives us the k. So let's put that in there. So I've got negative 2 times what? 4 squared plus 16 times 4 minus 1. Okay, so we actually compute that. That's negative 32, I think, plus 64 minus 1, and I get 31. Okay, so the vertex is what? 4, 31. By the way, I threw this in here, and I'll probably be asking you a question like this on the exam. Okay, is it a minimum or a maximum point? It's actually a maximum point because what? Okay, it's a y maximum point, if you want to throw that in, because what? This is a frowning parabola, right? It doesn't have a minimum point. It goes on forever down these ways. But what? That means it looks something like this. It's got a high point up here, 4, 31. Okay? Let's do another one. Find the vertex of y equals, I gave it this name, g of x this time, so you don't have to get hung up on f of x here. But it's x squared plus 2x plus 3. Okay? You can see this time what? A is 1 and b is 1. Negative b over 2a would be negative a half this time. Then I've got to what? Compute the value of that function, that quadratic function, at negative 1/2. So that would be what? Negative a half squared plus negative a half plus 3. Okay? And if I did my math right, that's a quarter minus a half is negative a quarter. 3 minus a quarter is 11/4. Okay? So this would be what? The vertex would be negative 1/2, 11/4. Okay? So sometimes we could get fractions in here. I've just been nice so far and haven't given you any of that type. This is actually a minimum point for this parabola because it's opening upwards. Notice that the leading coefficient a is equal to 1. That means it's smiling. That means it has a low point there, right, at those coordinates. So that's a low point or y minimum point. All right? Okay, so it's very easy to use the formula here, and it shouldn't be that hard to remember. You just got to remember what the x-coordinate is. The y-coordinate you should be able to figure out logically, since it's a point on the function, that y should be the function evaluated at that x-coordinate, right? Okay, should be easy. Want to throw in one last thing. You've seen this by looking at graphs of parabolas. There is a line of symmetry, okay, to a parabola. The vertical line through the vertex of any parabola is a line of symmetry for the parabola. Okay, so we've seen pictures of this before. So if I've got some parabola that looks like this, and I've got what? And I've got the vertex down there. There's going to be a line of symmetry here for that parabola right through the vertex. What do I mean by a line of symmetry? Well, to not put too fine a point on it at this right now, it means if I was to take, for example, a mirror and to lay it along that vertical line, the right half of the parabola gets reflected right onto the left-hand side, right? In other words, the parabola, they're mirror images. The two sides of the parabola are mirror images of each other across that line. Okay, and I just want to show you why that's true. Okay, so let me throw that in there. Since the parabola we are generally naming generically as HK, the vertical line through that would be y equals h. Okay, so that would be the line of symmetry for that parabola. Okay, y equals h. Now let's prove that. Why do you get symmetry here? Okay, suppose x is equal to h plus delta. Okay, so I'm thinking about this in terms of x coordinates here. I'm not at h, I'm at some little change. Changes are often written by deltas, okay, here. So here, I'm just going to have a delta. Some people might like to write delta x, a change in x, but I just wrote it as a single change, delta. Okay, I just gave it a name, the change. Okay, or the difference, delta. X is h plus delta. Now, if I evaluate the function at x plus delta, I would have what? A times x minus h squared plus k. So that would be h plus delta minus h, and then square the difference and add k. So that would be a delta squared plus k. Okay? A delta squared plus k. However, if I go in the opposite direction, so suppose that x is equal to h minus delta, whatever delta is, positive or negative, you can see what I've done here. Okay, I'm going in the opposite direction from h that I did before, but just as far in absolute value. What would be the function evaluated at x minus, or h minus delta? It would be what? A times h minus delta minus h squared plus k, and that would be what? A times the quantity negative delta squared plus k. But negative delta squared is the same as delta squared, so that I've got a delta squared plus k. That's exactly what I've got up here for that result. So what I've written here is that it's exactly the same value at h minus delta as it is what? H plus delta, okay? The same y value, okay? Sort of, well, I should really write x and y here. So I've drawn another little picture here for you. Here's my parabola, okay? The low point in this case, the vertex, is hk, okay? Now, if I move a certain distance, delta, this direction, I go, okay, so I'm come this way in the horizontal direction, delta units, okay, from h, and I evaluate the function there. Or if I do what? H units in the opposite direction, so h plus delta, I come this way, h plus delta and evaluate the function here, I get the same y value, right? That's what that's saying here. So I get the same y value. So if I move the same distance either direction, to the left or the right from h, I always get the same y value. And that's precisely why I'm getting symmetry with respect to that line, y equals h. Okay? Alrighty. Well, I hope you understood all this stuff. Okay? You'll be tested on it later. Okay?